Okay, I suppose we can get started. Any questions from anyone before we get going? Did I start recording? Yes, okay. Questions about final demos, final reports? Okay. Bruce? So the final report, I'll post a due date on Canvas. I'd like for everyone to have at least 1 week to work on it after their demo. And so that implies a due date. I'll post a specific due date, but it implies one that's around a week from next Friday. Our last demo date is a week from this coming Friday. And so the report will be due approximately a week after that. And if any questions come up as you start working on that, just let me know. Okay, anything else from anyone? So I'm thinking that Friday will be our last lecture of the semester, given that we'll start our demos on Monday. We'll just spend all of our time in the lab then on Monday. If you could try to encourage your classmates that don't typically come to lecture to try to come to the last lecture, I'd appreciate it. It just feels like an anticlimax on my side of the room if the last lecture of the semester is to like a handful of folks. So if you could help me try to get some people here for the last lecture, I would appreciate that. And those of you that are attending virtually, if you could try to walk to the lecture hall, that would be appreciated. So my plan for today, there are a few groups that are using FFTs in their final projects, and I've been receiving some questions about how to use an FFT in lab. And so I thought that I would give a lecture about this particular algorithm and how we use it. This is a challenging lecture to give. It's one that can easily sort of become more sort of mathematical than is perhaps useful. And so I've been giving some thought as to how to present this. The web page that I have up, I will just let you know, if you go to the course website, there is in fact a link here under Algorithms and Techniques titled Fast Fourier Transforms. That's the website that's up here. If you were to go to this website, what this website does, or what this web page does, is start from the sine cosine representation of the Fourier series, and from that sine cosine representation, it derives the C implementation of a fixed point FFT without skipping any steps. And so the full story does exist on this web page. I'm not going to attempt to go through that full story in lecture because I don't think that we have the time. What I would like to try to do, though, is to provide some information about the line of reasoning that takes you from this to something like this. Looking at these two things, it's not necessarily obvious how they connect, and so I want to talk about this just enough to hopefully illuminate the connection, and then you could go fill in the gaps by looking at this webpage and some other resources that I can point you to. But then what I want to spend a considerable amount of time talking about, hopefully, is sort of how we use a implementation like this. What are the trade-offs that we're thinking about when we're implementing an FFT? And how do we appropriately sort of navigate that trade-off space for a particular application? But I thought it would be kind of interesting to just talk a little bit about the path from this sine cosine representation down to this C-code. So where to start a conversation like this? I will just remind you, because I think for all of you it is in fact a reminder, because I trust that you've all seen this before, that probably it was the case in Calc 1 or Calc 2 that you got introduced to this expression here, the sine cosine representation of the Fourier series. And you probably, when you were introduced to this, you were told that what you can do with a Fourier series is approximate any periodic function by sums of sines and cosines. And perhaps it's a sum of an infinite number of those. That's okay. For other periodic functions, it may be a finite series. But you can approximate essentially any periodic function by way of these sines and cosines. And one of the first exercises that you probably did in that class is you started with this equation, and then the first question that was probably posed to you is, okay, we're going to approximate some function s of t by this sum of a whole bunch of sines and cosines. what are the amplitudes of all of those sines and cosines that compose that sum, the ANs and the BNs there. And one of the first exercises that you would have done is solve for that, solve for those expressions. And you did so, you may remember, by making use of the orthogonality conditions. These are some things that we know about how sines and cosines work. For instance, we know that the integral of some integer number of periods of a sine or cosine wave is 0. Hopefully that's sort of intuitive at this point, but of course that's the case. We furthermore know that the integral of the sum between sines and cosines is 0. Think of them as sort of canceling each other out. That would be the next orthogonality condition. And then finally, the product, I think I said sum. The integral over the product of two sines or two cosines is 0 unless they're exactly the same period, in which case it's a constant. And you will have used these three properties of sines and cosines and the integrals of their products in order to figure out those expressions for AN and BN and that compose this series. I'm going to skip through that algebra again because I think it's familiar, and it's there if you want to see it. But this hopefully looks sort of familiar to you, right? So if you have some function FFT that you want to approximate by a bunch of sines and cosines, you have to figure out the relative amplitudes, the absolute amplitudes of all of the sines and cosines in that expression. And you would have derived these two equations for how you get those coefficients. Does that sort of kind of ring a bell for folks? It may have been a while, but I trust that you probably have seen this before. Then it was probably the case that having done this, you then probably got introduced in a little bit more depth to imaginary numbers. And you would have made the observation that what we kind of have here is like a two-dimensional series, sort of. We have sort of the cosines and the sines. And so perhaps it doesn't seem like such a stretch that, well, maybe we could represent all of this information in a little bit more tidy fashion if we used imaginary numbers, which are essentially just 2D numbers, right? So if we represent all of this using 2D numbers, perhaps it's the case that we can bundle up all this stuff into one expression that includes only complex numbers. And so in order to do that, you were probably introduced to the Euler identity, that fascinating, equation, e to the I pi equals cos theta plus I sine theta. With the right choice of theta there, this is that expression that gives you a single equation that includes e, pi, I, 0, and 1. It's just kind of crazy. So in any case, you were probably introduced to this equation that relates complex exponentials to sines and cosines. With that equation, you can rewrite cosine and sine of theta in terms of these complex exponentials, which means we could go back to our sine-cosine representation of that Fourier series and substitute in these equations that involve complex exponentials everywhere that sines and cosines appear. And we would end up with the following, which we could bundle up very concisely into this expression where that now it's the case that the coefficients associated with each of the complex exponentials in our series are themselves complex numbers. That's okay. So depending on the value of n, if it's equal to 0, c is this. If it's greater than 0, it would be this computed from the ANs and BNs. If it's less than 0, it would be this computed from the ANs and BNs. And so what this tells us is if we go through the work of computing the sine and cosine coefficients, we can, from those coefficients, compute the complex exponential coefficients, but that's a little bit annoying. And so what we would really like is an orthogonality condition for those complex exponentials so that we can solve a little bit more directly for the complex exponential coefficients. So in other words, so that we don't have to solve for the sine-cosine coefficients in order to then arrive at the exponential coefficients, we can just go directly there. And so what we really want is to answer that question. If we take the product of a complex exponential and its complex conjugate, what is the orthogonality condition that pops out here? And you can turn the crank on this, and you end up reusing those sine-cosine orthogonality conditions from before, because, of course, we can turn these into sines and cosines, and so we end up with integrals of products of sines and cosines, and we know things about how those integrals behave from the orthogonality conditions that we already sort of talked about. And so ultimately, you can arrive at the following orthogonality condition. A complex exponential times a conjugate, where the only difference between these two expressions is m or n in the numerator of the exponent there, is 0 unless m and n are equal, in which case it's a constant. So this is our orthogonality condition for the complex representation of the Fourier series. The thing to keep in mind here is that this representation of the Fourier series and the sine cosine representation, it's the same information. We're just representing that information mathematically a little bit differently, but they carry the same information. It's just kind of handy to use the complex exponentials because we sort of have 2 dimensions here, so why not use 2D numbers, and we get sort of tidier expressions. So then with that orthogonality condition, we had previously solved for some expressions for the complex coefficients as functions of an and bn, the sine and cosine coefficients. Now we can solve for an expression for those complex coefficients sort of directly. We can solve direct from the function that we are trying to approximate. We multiply by e to the negative 2 pi mi over t naught times t, 1 over the period of the function, and out pops our complex coefficients. Again, I think that this is probably relatively familiar to folks, and so you may remember these 2 expressions from a discussion in one of your classes about Fourier transforms. But again, carries the same information as your old friend sine and cosine. Okay. But this is an integral operating on some continuous function f of t. In our case, in this class, it's probably the case that if you're computing an FFT on something, it's probably on discretely sampled data. Maybe it's the case, for instance, that you're using the ADC to sample a microphone at some rate, so you're gathering a bunch of discrete data points, and you'd like to Fourier transform that discrete function to answer the question, what frequencies are present in this buffer of microphone data that I have gathered? And so what that implies is that we need a discrete representation of this Fourier series. We want to change these integrals to sums. So how precisely do we do that? Well, what we would really like to do, we only gather a buffer of some size. For purposes of this explanation, I'm saying that the size of the buffer of data that we gather is 2n. It'll become clear in a moment why I chose 2n and not n. It just makes for slightly tidier equations. But we're gathering 2n data points into some array, perhaps. And what we'd really like to do is change this representation of the Fourier series over continuous functions, which you can see sums n from minus infinity to infinity, to instead, we're approximating f sub k, now a discrete function, and n only goes from 0 to 2n minus 1, the size of our buffer. But as before, we have some summation over some complex coefficients times the same exponential there, except now t is not continuous, it's t sub k. It's the time at which each of these samples was actually gathered. So just to be clear, we've made the following replacements in attempting to move from the continuous representation to the discrete representation. The function that we're approximating goes from a continuous function of time to instead a discrete function, where time is indicated by the index k. Instead of summing from minus infinity to infinity, we're going to sum over our number of samples. T is no longer continuous. Instead, it's discretely sampled. And if we've gathered 2n samples, then we gather it, and we assume that those samples are gathered equispaced. Then we can solve for each of those t sub k's as a function of the total time and the number of samples that we've gathered. But what we don't yet know is what's the discrete version of c sub n here. And so that's what we need to solve for. In order to solve for that, what we really want is an orthogonality condition for this discrete representation of the Fourier series. We know it for the continuous representation. We solved for it previously, making use of the orthogonality conditions from sine and cosines that we talked about way at the top. What we want is to answer this question. Instead of doing the integral from t naught to t naught plus beta t naught over the whole period. Now we're doing this summation. And the question is, what is sort of the equivalent equation represented discretely rather than continuously? What is the orthogonality condition that pops out here? We have to solve for this to figure out what that actually is. And so that's okay. We can do that. So we can take a look at this expression. We notice that we have a product of exponentials here. So of course we can rearrange this into a single exponential where we're summing their exponents. And that gives us this expression here. We have an expression for t sub k because we're assuming that all of our samples are gathered equispaced in time. And so we can simplify this even a little bit further to the expression shown here. And then something clever happens, or at least I think it's clever. Perhaps it's the case that mathematicians that do this kind of thing a lot, this is obvious to them. But when I first saw this, I thought, wow, it would take me a long time to notice that. What was noticed then is if you look at that expression and make some new variable r that is defined as e to the I pi over n, big N, times little n minus little m, then this rather complicated looking summation reduces to the following, which is a geometric series that has a known solution. And so you could look at that and you go, oh, that's a geometric series. We know that the solution to that geometric series is the following. And so we can just write that down. And then we substitute back in that expression that we had defined for r to end up with this final expression here, which is moving us in the direction of an orthogonality condition. Then finally, and I know that this is kind of this is a lot of information quickly, but I just want to illuminate the chain of reasoning because it's really interesting, I think. So we end up with this expression, and then we stare at it for a while. And when you stare at things for a while, you're trying to write things down in different ways to see if anything sort of pops out to illuminate something to do. One of the things that might occur to you to do is to say, well, we have some complex exponents here. Because of Euler's identity, we know that we can write those down as a sum of a sine and a cosine. So let's just do that and see if we notice anything interesting. So let's look specifically at the numerator here, 1 minus e to the I2 pi n minus m. We can use Euler's identity to write that down as the following sums of sines and cosines. Then we can notice we have the sine of 2 pi times some integer. That's always going to be 0. Sine of 2 pi times any old integer number is always going to be 0. So that third term just goes away. That's just 0. And then furthermore, the second term here is cosine of 2 pi times some integer. That's always just going to be 1. So that second term just goes to 1. And so that implies that the numerator of that expression is always 0, always. Which means this whole expression is always 0 unless the denominator is also 0. In which case it's something else. So then we can look at the denominator and we ask the question, when is the denominator 0? The denominator is 0 when n minus m, that quantity there, is 0 or plus minus 2n or plus minus 4n, et cetera, et cetera, et cetera. But we've only gathered 2n minus 1 samples. And so the only condition under which that denominator is 0, under which it could be 0 given the amount of samples that we've gathered, is when n is equal to m. Otherwise, it's always 0. The whole expression is always 0. When n is equal to m, the whole expression is not equal to 0 because both the numerator and denominator are equal to 0. So some other number could pop out here. And indeed, if we substitute n and m being equivalent here, this of course simplifies to just e to the sum from k equals 0 to 2n minus 1 of e to the 0, just 1, right? And out pops 2n. And so we arrive at an orthogonality condition for the discrete representation of this. We were seeking the answer to this question, right? What is this summation? And what we have found is it's always 0 unless n and m are equal, and if they're equal, it's 2n, the number of samples that we've gathered. Which we can then use to solve, like we did previously. Now that we know this orthogonality condition, we can solve for the expression for all of our complex coefficients for the discrete representation of this Fourier series. Okay, so in summary, we arrive at the following. This, I'm not sure if this is familiar to folks or not. I'm not sure if people have been exposed to the discrete representation of this explicitly or not. Okay. So we should pause here and just think about this for a moment. Let's suppose that you gather, this, by the way, has not been optimized yet. I'm going to talk about the cleverness that led to the fast Fourier transform. This is still just a discrete Fourier transform, which, as we'll see in a moment when we talk about the computational expense, we'll notice that as presented thus far, the complexity of the algorithm being presented here is of order n squared, which means it's not really practical. I'm going to point out the clever observation made by Tukey to speed this up to of order n log n. Actually made this a practical algorithm. But let's pause for a moment and think about this. So let's suppose that we gathered, how to talk about this. Okay, so let's suppose that you've gathered a buffer of data from, say, a microphone, and you've computed the FFT of that microphone data. The questions that you are probably asking yourself for your particular application include things like, what is the highest frequency that I can observe with the FFT that I have computed? Your FFT, well, for now it's still just a discrete Fourier transform, it will become an FFT, is composed of a series of bins that tell you effectively the amount of power in each of these frequency ranges. So another question you're probably asking yourself is, what is the size of each of these bins? So when we transform to this discrete representation, what ends up happening, well, let me just tell you and then maybe I can justify it. So the first question, what is the highest frequency that I can resolve? This is a question related to the Nyquist sampling theorem. People know the answer to this? So let's say that you are gathering data at 50 kilohertz. What's the highest frequency that you can observe if you were to Fourier transform that? 25 kilohertz. You can observe signals up to half as fast as your sampling rate. If you're sampling at some speed, k hertz, you can observe frequencies as fast as k over 2. So what that implies is if you are interested in observing frequencies up to some rate, that informs your choice of sampling rate. If you need to observe, if you need to be able to answer the questions, are there frequencies as fast as, say, 25 kilohertz present in my signal, what that implies is that you must sample that signal at least twice that speed. And in fact, you probably want a considerable amount of margin. Probably actually want to sample it like 5 times as fast. And then there's the second question. Let's say you gather, 512, a buffer of size 512 that you're going to compute a Fourier transform of. And let's suppose that you are transforming audio data. That is to say, the input to your Fourier transform is pure real numbers. You transform that. You know that you can observe frequencies up to half as fast as your sampling rate. The question is, how is the information about the power in these various frequencies distributed throughout the bins in the output of your FFT? Again, let me just tell you, then I can perhaps justify it. So for real valued input, the output of your FFT is mirrored about the halfway point through your output buffer. So you send complex numbers into the FFT, an array of complex numbers gets sent into the FFT, an array of the same size, complex numbers, comes out of the FFT. It's converting complex numbers to complex numbers, right? They represent something different now. Now you're in frequency space, but the same size array comes back out. The first half, the output of the FFT for pure real valued numbers is mirrored about the halfway point through that array. So the information that you probably care about is contained within the first half of that array. So let's say that your buffer is of size 512, and let's say that you gathered that buffer at 10 kilohertz. What that implies is that there's information in the output of your FFT about frequencies up to 5 kilohertz. That information lives in the first half of the output buffer. So how much frequency is contained within each index? Well, the answer to that would be, double check my mental math on this. It would be 512, the total length, divided by 2. That'd be 256. That's the number of indices you have, divided by, in the example that I'm giving, 5K, because that's the total amount of frequency contained in all of those bins, which implies that the amount of frequency contained within each bin would be 5,000 divided by 256. So what does this have implications about? Well, if you're trying to use an FFT to, for instance, resolve notes being played in music, the question you have to ask yourself is, how far separated are the notes that I am trying to observe in my output FFT? Because you better choose a buffer size that actually puts the notes that you care about into different bins so that you can distinguish them. So the fundamental trade-off that you're making here is frequency resolution versus time resolution. The smaller your buffers, the more often you can compute the FFT on that buffer, which means you're getting an output from your FFT more frequently. You have better time resolution. The consequence, though, of having a shorter buffer is the amount of frequency contained within each bin of the output of your FFT is greater. On the other hand, you could have a big old buffer where you're gathering a whole bunch of, say, microphone data. Once it fills up, you compute the FFT on it. What that implies is that it takes longer to fill up that big buffer, so you drop your time resolution, but because you've gathered more data, you get more frequency resolution in the output. There's a smaller range of frequencies contained within each of your output bins. And so when you are when you're implementing something like this in your program, what you're asking yourself is, what's the highest frequency that I need to resolve? That's how you decide upon your sample rate. Then furthermore, what you're asking yourself is, with what resolution do I need to be able to figure out the frequency components in whatever the time domain signal is that I'm interested in? That is how you will establish your buffer size. The greater the frequency resolution you require, the smaller the time resolution that you get. Does that make some sense? So it's all a trade-off. It's a hard thing to describe. I'm doing my best here. But one of the things I just wanted to point out is, so as presented thus far, we have not yet talked about the fast Fourier transform. We've just talked about the discrete Fourier transform. If we stay in the discrete Fourier transform world here for a moment, we could ask the question, what is the complexity of this discrete Fourier transform algorithm? Well, let's suppose that we've gathered, a buffer of length 2n, and we want to compute the discrete Fourier transform of it. We can write that down as a multiplication of a matrix by a vector, right? The matrix is of dimension mk. We have an output vector of length m, right? And we've gathered, n of these samples. The upshot here is that the computational expense of the discrete Fourier transform as presented is n squared, which means it's effectively impossible to implement this in real time. This was the state of the world, correct me if I'm wrong, Bruce, when you were in college. Is that right? First year you were in college. What that implies is that before that, it was not possible in real time to compute the discrete Fourier transform of time domain signals. That, by the way, is there's some interesting resources to read about this. That fact is of unbelievable consequence. The fact that this was not possible, there's a good Veritasium video about this, but effectively, the fact that this was not possible had a massive impact on the state of nuclear armament around the world. What it meant, just in brief, is that it was not possible to, in real time, compute discrete Fourier transforms on seismograph data, the equipment that's used to measure earthquakes. What that meant is that it was not possible in real time to know whether somebody on another part of the world, in another part of the world, had detonated a nuclear weapon underground. There were ways that you could know if somebody had detonated a nuclear weapon on the surface of the Earth. There were ways that you could know if they detonated it under the ocean. There are ways that you could know if they detonated it in space. There was not a way to know if you could detonate it underground, because you couldn't, which meant you couldn't really prohibit it because there was no way to know if anybody was following that rule. What that suggested is, if what I'm about to describe had been possible at that point, it is conceivable that they could have actually prohibited nuclear weapons testing and known whether people were following those rules. Because this was not yet possible, they couldn't test it, they couldn't practically prohibit it. It didn't mean anything, because you couldn't know if anybody was actually following the rules. If what I'm about to describe had been known at this time, the state of the world could be really different, really, really different. So it's too complicated. So what's the observation? What is the clever observation that takes this ultimately from order n squared down to order n log n? It's the following. To my understanding, Tukey was staring at that expression. That's a summation. This is the summation that we just arrived at that tells us it's how we compute each of the coefficients associated with the terms in our discrete Fourier transform, right? It's each of our C sub m's. What was noticed is, because this is a summation, we can break this into the sum of two summations. That's perfectly allowed. We could think about this as being the sum of the even terms in that whole collection of terms that compose that sum, and the sum of all of the odd terms, f sub 2k plus 1 of all of those terms. You'll notice that each of these two summations now only goes half as far, right? Because we're only summing over half as much stuff. And in particular, we have split that big long summation into its even parts and its odd parts. And then you look at this and look at this second term, and what was noticed is, well, we could factor out a term here, e to the minus 2 pi I over 2n times m. We factor that out, and what we are left with is exactly the discrete Fourier transform of the even parts of that big expression. That is exactly the equation for a discrete Fourier transform of a smaller buffer, a buffer half as big, right? But it's exactly the same equation, plus exactly the equation for the discrete Fourier transform of another half as big buffer, this one on the odd components, multiplied by some coefficient. So we could rewrite this as our equation that computes all of these amplitudes is 1 over 2n, our total number of buffers, times the discrete Fourier transform of the evenly gathered terms in that buffer, plus some number times the discrete Fourier transform of the odd components. This was the observation, because then you can carry on. You say, all right, well, now I'm going to take each of these, and I'm going to split them into their even components and their odd components. Then I'll take all of the results and split those into the even components and the odd components. The observation that was made was that if we choose a buffer size that is a power of 2, then this whole thing boils down to discrete Fourier transforms of length 1 buffers. When you get all the way to the bottom to a length 1 buffer, and you ask, how do we compute Cm, the complex coefficient, if our buffer is of length 1? Well, now that summation goes away because it's a summation over one term, right? Furthermore, k in that equation is 0, because our summation starts at 0, what we're left with is 1 over 1 times e to the something times 0, so that becomes 1 times f naught. What this shows you is that a length 1 transform just copies the input to the output. So what that implies is if you break this discrete Fourier transform of some big old buffer, but it's a buffer of length that is a power of 2, break it into half, 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 the whole way down, and you get all the way down to length 1 transforms, you're just copying the input to the output. Very computationally cheap, right? So what this implies is, so let's suppose, for instance, right, that we only gathered 8 samples, and we have split those 8 samples once into 4 and 4, then we split them again into 2 and 2 and 2 and 2, and then we split them again into 8 length 1 transforms. We end up with the following. And what you will have noticed is that the length 1 transforms, all that they do is rearrange the inputs. Here's our inputs. These are our samples from, oh, say our microphone, right? At time 0, 1, 2, 3, etc., up to 7. For length 1 transforms, all that it does is give us the same size buffer on the output, but rearranges it a little bit. But what's powerful about this is because we have this expression, right, that represents our discrete Fourier transforms of some size buffer as being the sum of discrete Fourier transforms of smaller buffers, once we've got the length 1 transforms, we can build up to the length 2 transforms just by adding. Then we can build up to the length 4 transforms, again, just by adding. And you can build yourself the whole way back up. So what Cooley and Tukey did is notice a regression. They noticed they could split and split and split, and at the bottom of the regression is a length 1 transform. And furthermore, they noticed that the length 1 transform is easy. We just rearrange it, and once we've got it, we can use it to then build everything back up. The consequence being that the total complexity of this way of computing the FFT, mathematically the same, is n log n. Suddenly this is possible to do in real time. I mean, this has since become like arguably one of the most foundationally important algorithms for modern civilization, right? It's everywhere. It is possible because of this observation. And so like I said, once you've got the length 1 transforms, you can find your length 2 transforms as by linearly combining your length 1 transforms, right? Out comes your length 2 transforms. And then you go on and on and on. So basically, you're boiling it down to length 1. Once you've got the length 1, which is just rearranging your inputs, you build it back up, which involves adding things together and multiplying by known coefficients. Easy to compute coefficients, pre-computable coefficients, as it turns out. So, very, very briefly, let's just think about this step by step. Because I want to try to lead you to the connection between that C code and the original implementation. So let's suppose that we gathered 8 time domain samples that we would like to compute the FFT of. For generality, I'm supposing that our samples are indeed imaginary numbers that have non-zero imaginary parts, possibly. Okay, so that is just to say we've gathered 8 samples organized into their real components and their imaginary components. Like I said, for audio input, it's probably the case that all of your imaginary components going into the FFT are going to be 0. Okay, but let's just suppose that you've got 2 samples here. The first thing that we're going to do is compute the single point transforms, which, as we talked about, just rearranges these. And actually, as it turns out, it rearranges them in kind of an interesting way. I alluded to this earlier. The way that you figure out where each of your inputs to the 1 point transforms maps to the output is you consider the index of that input written in binary, and then to figure out the index that that input moves to in the output, you take that binary and you reverse it. There's a good reason for this, of course, but it's a good trick to know that, for instance, the index 1 input here, written in binary as 0, 0, 1, that maps to the output 1, 0, 0. Likewise for all of them. Okay, so to compute our single point transforms here, all that we do is move the inputs to the correct output locations. And so here, for instance, is a little bit of C code that does that. This, the observant of you may have noticed in the FFT implementation that we peeked out at the very beginning of lecture, this is the first thing that happens in that function. This is the computation of the single point transforms. All that it actually does is do a bitwise reorganization of the inputs. Then once we've got those single point transforms, we can use them to compute our 2-point transforms. This ends up looking like, think about it as a matrix operation here, okay, where we have our coefficients here. These are associated, you may remember, with the odd terms. You may remember that when we represented this as the sum of the even and the odd parts of that big summation, the odd ones had some coefficients associated with them. Here are those coefficients, right? But from our single point transforms, we can compute our 2-point transforms. Here's what this would look like in code. Which we could talk through, I suppose, but you know, it's not so hard to encode. And then so on, we can get our 4-point transforms, our 8-point transforms, and ultimately a generalized code where you get to specify the size of your buffer, better be a power of 2, but you get to specify it, and this will compute the FFT of that buffer. This particular implementation, I'll just mention, this particular implementation, you will notice, takes pointers to 2 arrays as inputs, both fixed point in this particular case, one of which represents the real valued input to the FFT, the other of which represents the imaginary input value to the FFT. They're both the same length, and it is assumed that the indices map the timestamps for each of these discretely gathered samples. Like I said, for audio input, Fi is going to be an array of zeros. What this then does is it will repopulate the arrays that you have passed in as input with the output of the FFT. It does an in-place replacement of the time domain content in the input arrays to the frequency domain output of the FFT. It rewrites them to the same place. It wouldn't have to work that way. That's just how this one happens to work. Okay. And by the way, last thing I'll just mention, if you're computing FFTs, you might also want to compute inverse FFTs, maybe. An inverse FFT, it turns out that with extraordinarily little change to your code for computing the FFT, you can instead compute an inverse FFT. All that it requires is that there is no sign reversal on the imaginary term. That is to say that that negative sign there is absent, right? So we don't negate the imaginary term. And there's a difference in the leading coefficient here. You'll see that this one has a 1/2n out here, this one does not. And so that implies that we eliminate a right shift that is present in the forward FFT that is not present in the inverse. But otherwise the code looks exactly the same, which basically means you could add like one more parameter here to tell the function whether you'd like for it to compute an inverse FFT or a forward FFT. And with 1 or 2 places in here where you add a little conditional, it could do both. Any thoughts about this? Questions? It's a challenging topic to cover, particularly in only one lecture. In the event that you've talked about these sort of derivation of FFTs in the past, I expect that you probably did so over the course of, I think, at least a week, in order to really spend the amount of time that each of these steps deserves on that step. But what I hope I'm illuminating here, what I'm trying to illuminate is if not every step that takes you from that expression to this function, at least the line of reasoning that takes you from that expression to this function, and a resource that allows for you to fill in the gaps if you care to. And furthermore, some ways of thinking about the trade-offs that you're always performing when you're actually implementing an FFT for some real application. Whenever you're doing this, you're computing an FFT because you care about the frequency content of some signal. So the first question you're asking yourself is, well, up to what frequency? Again, that sets your sample rate. The next question you're asking yourself is, what is the frequency resolution that I require? With the understanding that increasing frequency resolution costs you time resolution. If you want to improve your frequency resolution, you can't compute the FFT as often as you otherwise could. You're trading these two things. There's something else I wanted to mention about this. Oh, I know what it was. What happens if the signal that you're computing the FFT of has frequencies above the Nyquist rate? So let's say that you are gathering samples at 10 kilohertz, which means that you can observe frequencies as high as 5 kilohertz, but that the signal that you're computing the FFT of has frequency content up to 8 kilohertz or 10 kilohertz or 20 kilohertz or 20 kilohertz or higher. What's the consequence? That power doesn't go away. The consequence is it aliases. And so what you'll observe is you compute the FFT of this signal, and let's suppose that your signal contains, no power at any frequency except like 7 kilohertz, and you're sampling it at 10 kilohertz, which means the highest frequency that you can resolve is you're sampling it at 10, so the highest frequency you can resolve is 5. What you will observe is a big old spike of power somewhere. You could actually figure out where, right? But the consequence is that that power that exists at frequencies that you can't resolve gets remapped into frequencies that you can resolve. And so you become confused. You don't know if what you're looking at is in fact power at, say, 3 kilohertz, or if instead it's power at some frequency that is higher than your Nyquist sampling limit that's getting remapped back down to 3 kilohertz. An interesting experiment that demonstrates this is I have some Pico code down here that will compute real-time FFTs on microphone data. If you were to send a pure sine wave into this by way of just like a signal generator, started it at a very low frequency, what you would observe is a big old spike at the beginning here. And then as you turn up the frequency, you would observe that spike move up through the FFT. And then you start to exceed the Nyquist limit, and it starts just moving on back down through. And so the other question that you're asking yourself when you're implementing something like this is, well, what's the highest frequency that I care about? Furthermore, what are the frequencies that are present in the signal that I am computing the transform of? What do you do if you care about frequencies up to some threshold value in some signal that contains frequencies above that value? How do you mitigate this? Any thoughts? You have to enforce that by the time that signal gets to where you're sampling it, those higher frequencies have been eliminated. How do you do that? A low-pass filter. And so if you want to prevent this, what you'll implement is an anti-aliasing low-pass filter, where you've made a decision about the highest frequency that you care about in this signal, and so you've put that signal through a low-pass filter that attenuates out anything that might be there above that frequency that you care about. Then you sample it. and you sample it at a rate that makes that highest frequency that you care about observable. At least 2 times faster than that frequency. Probably you want margin, right? So probably even faster than that. But you get those frequencies out of the signal before they get to where you're sampling it. And that will prevent the aliasing. Bruce?
That says that the select sample that filtering has to be analog, not a digital filter.
Right.
Always in the lab, there is frequencies you don't expect that are high. Somebody, two rows over one. In the microphone, it's quiet. Always low pass. Care about the power.
And that noise is coming from everywhere. I have the lights in the lab are kicking out noise at, if I remember correctly, it was something around 20 kilohertz or something like that. By the way, how do we know that? Because we put the scope into FFT mode and left the probe disconnected. So now the probe's just an antenna. So we're computing the FFT on the power that the probe is picking up as an antenna. There's a spike at 20 kilohertz, or wherever it is. I can't remember exactly. You kill the lights in the room and the spike goes whoop. So there's noise coming from all over the place, which just implies, as Bruce suggested, you always want an anti-aliasing low-pass filter. Okay, I will be in lab this afternoon. There may or may not be a very tiny guest in lab this afternoon. I'm not sure. We're doing some improvisational childcare puzzle solving, so I might have a baby dangling off of me in lab. I don't know yet. But in any case, I'll be there, and I'll see many of you there. I'll see the rest of you on Friday. Like I said, if you could help me try to get folks here for Friday, I'd appreciate it.